Right, guys. Today this is our second presentation on differentiation, and I hope you have looked at the previous presentation, so that when you start from here, you've got some kind of continuity. But I will just remind you briefly. I think when we stopped, we were discussing this type of situation. You had already looked at instead derivative at a given particular point, and I looked at the standard derivative at a generic point x, and we said this is how we calculate it using this incremental quotient here. And then this is the notation. You can say df of x dx, or f prime of x, meaning the derivative of f. Now, I think this is important. Right, this is important that what I mean is important is you must notice that when you have a notation like this, dy dx, we also, just without any explanation, you must be able to make sure, to be clear that this is the independent variable of y. If in case the function comes in another different variable, like f of t equals to sine 3x, then dy dt there, that t there, tells us that that's the independent variable of what? Of the function. And that's very important. Later when you're dealing with differential equations, you must be able to be given a differential equation and be able to tell exactly what's the independent variable, what is dependent variable. Then when you solve, you know what to do. That is very important. All right. Now, for today, like I was saying, we're continuing with our presentation, but in this case, we're going to look at these types of functions. Our focus today would be polynomial. I said there are polynomials and more, but we're mainly with polynomials here. Now, before we go any further, look at this. I've written there almost like six versions or six type of, I don't know what to say, six expressions, but all of them, I can say they belong to the same class of polynomials. I hope you remember this expression here is a binomial. So if we continue increase these terms, binomial, because there are two, but in general, if we deal with any number, we say those are polynomials. But what must be clear to you, you must notice that all these functions from number 1 to number 6 there, they are functions which are built up from these building blocks. 1, x squared, dash 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 x n dash 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 up to wherever we want. I mean, if we stop at xn, then we've got a polynomial of x of order n. But if we just have this one, that's one term, the monomial, and we multiply by c, then we get a constant function. In other hand, if you've got this one only, and don't multiply by anything, get a linear function like this. But if you multiply by a number, we can get something like mx here, and that's m is what a gradient of that line. Altogether. So these functions, which you call polynomials, they're built up from these things by adding them. In the general case, we've got something like this. If n here, an is not equal to 0, then we've got a polynomial of degree n. But when we've got a constant like this, it means all these coefficients are 0. We're only left with a1, which will be the constant function. You must more or less understand something like that. So we are going to deal with these things individually. We start from the constant, move from there. Some of them I'm going to omit for you to do, but I think by the time I start omitting things here, it should be very easy for you to proceed as you have seen in previous examples. Now, let's start. Now, there is this. The first function we're going to get is a constant function. Now, the constant function, remember, the definition of a derivative, according to what we've seen, is f prime. We're calculating this at a generic point, x. f prime is equal to the limit as delta x is going to 0. Then our denominator always here is delta x. Then if we evaluate this function, we'll say f of x plus delta x minus f of x. But at this point, we must all understand what we mean by a constant function. All together, we must understand what we mean by a constant function. Then let's say we have something like this. We've got a vertical axis there, a horizontal axis there. Then that is our x-axis, and that is our y-axis. Constant c is just a real number. C is a real number. So if c is a real number, now this function says for every value of x, at each value of x, this function will assign a c. Now it's a constant. So I'll set x there. You want to say c. C is a real number. So for every value of x to assign c. So if c is there, there is c. Or c is there, could be there. That's just a constant. So if we pick 0, f of 0 will be c. So that would be the value of the function there. We go to 1, f of 1 will be c. So it will be 1, and there it will be 1 comma c. So at the end of the day, what we have actually is a function which has got a graph which runs through like this. Through c. That's the thing. That's a constant function. So now, what we're doing here, we say a derivative was the rate of change. That's what we're saying here. When we calculate this limit, we now say limit delta x going to 0. This value will be c. That value will be c. So c minus c over delta x. Remember, delta x is not equal to 0. Delta x is not equal to 0. What we only emphasize that it tends to 0. We can take it as small as we wish altogether. So, but if we take a number as small or as big, never mind how big it is, and we divide, use that number to divide 0 because the numerator is 0, then the answer will be 0. So what we're doing here, we're precisely calculating the limit as delta x is going to 0 of 0. But 0 is a constant. It doesn't matter whether delta x tends to 2, tends to infinity, or tends to Honolulu, 0 will be 0. So this is 0. So what is the message from this calculation? The message from this calculation just says that the derivative of a constant function is 0. But what's the derivative? It's the rate of change of function. The function is constant. Is it changing? No. So the rate of change must be 0. That is very clear. Is that right? So you must, I think if you want to forget everything in this topic, at least you must be left with this idea that the rate of change of something which is constant is 0. The derivative of a constant function is 0. Is that clear? I hope that is clear. Any question at that point? Right. So if there are no questions, then we'll proceed to the next session. Let's proceed to the next example, next discussion slide. Let's see. Now we've got here a linear function. A linear function, in this case, we know in general a linear function is y equals to mx plus c. In this case, when we've got this one, we can say this is 1x. I'm just writing there 1. We normally write just x, but I'm just writing explicit there so that you can see how it relates that. Plus 0. So it's a linear function which passes through 0. That is it. So similarly, let's see what happens here when we get, we want to compute our derivative using that incremental quotient. So we give this delta equal to 0. This is over delta x, then we got there. Now I'm going to evaluate this. Remember, always we're evaluating this at point x and at point x plus delta x, those 2 points. So now if you evaluate this function is an identity function. It says, whatever you give me, I take it out as the output. So give me x, I'll give you x. Give me 2, I'll give you 2. So if you give this function, input this function x plus delta x, it's going to give you x plus delta x. Is that clear to everyone? Then minus x. So simplifying, going further, delta x going to 0. These two terms are like terms, this one and that one. And they only differ by the sign, so the produce us a 0 there. 0 plus delta x will be delta x. So at the end of good day, we've got delta x over delta x. And be careful that we can't do the plugging in of 0 because we're going to get that in undefined entity. But if however small delta x is, you divide it by delta x, you must get what? 1. So we are precisely calculating the limit of delta of 1 as delta x is going to 0. Like we saw before, this is a constant. It doesn't matter how small x is, whether x tends to 0, 2, whichever number, 1 will be 1. So then the limit here will be 1. Now, what I wanted to try to do there is to look at this one carefully and see that is the same one we got there. And that one there, as you know it, that is the gradient. That's the gradient of that straight line. All together. So what I want you to do, you can do something similar with any other line. Let's say you get 2x plus 4. Do this, and you should actually expect to get that m. In other words, what I was saying, if we're given a linear function y, mx plus c, we should know that derivative of y with respect to x is actually m. What's the message? The derivative of a straight line function or linear function is this gradient. And once that fact is sitting squared in your head, there's no need really even to calculate it. When I give you an equation of a line, what you can do, you can actually extract the derivative and say this is the derivative from that. If it's not given exactly this way, because I can give the equation of a line maybe in an implicit way, like this is explicit, I can give it in an implicit way, something like this: y plus 4x equals to 6. This is still a equation of a straight line, but it doesn't give us m in an obvious way. Then we say this is given in an implicit way. So if I know this is a case of a line is given in implicit way, the only thing is to express it in an explicit form. Then I don't even need to calculate the derivative. I can just extract the gradient and say, here's the derivative. Is that all right? So those are the APC stories, which, I mean, anyone who's done this type of mathematics, even if you pass or fail or forget all what you have learned, these are some of the things which you should remain with you for maybe for the rest of your life. Like everybody remains with the fact that A is the first letter of the alphabet, whether you pass writing composition or you don't. But if you even forget that A is the first letter, then that's what it becomes a disaster. Okay. Now, any questions there? Okay. Let's proceed to the next example. One thing which I wanted to focus on here, as we move forward, you must focus on, try to see if there are patterns coming up. If there's something which is coming up consistently. Are we together? Then from there, when we sort of summarize those observations and those patterns, we must extract some piece of knowledge there of mathematics, and that is important. Are we together? Okay, let's do this one. Let's say we want the limit, the derivative of f as a limit of the incremental quotient. I hope you remember, I think I mentioned this before. This expression f of x was at delta x minus f of x over delta x is called incremental quotient. But now we are evaluating this for this function, which means we immediately can write here limit as delta x is going to 0. Delta is going to 0 of x plus delta x. What should I write there? You can tell me. X plus delta x. It says all squared minus x squared. It's very important that you know how to evaluate a particular function given. Otherwise, you're going to come up with something which is not making sense. So then, this is a binomial, a plus b squared. I think that is a kind of chorus of everybody who's done math as grade 12. A squared plus 2ab plus b squared, isn't it? So our b is delta x, our a is that. So let's continue that. Delta x then our polynomial gives us a plus 2x delta x. Like I repeat here, this x and that x, they are related or not close related. You cannot simplify that as x squared. Okay. This is not x, this is delta x, change in x. So plus change in x all squared minus x squared. Listen, I'm not saying really maybe you're going to be asked to do this kind of a thing, but I'm doing it for the sake of you getting some kind of idea that these things can work them out. And once, even if you're going to get to summarizing and using formula or using some kind of rules, you must have an idea where these things come from. Is that right? Not that maybe the teacher brought them from his pocket, then they're fine. No. So this term and that term again, they make 0. Then what we're left with? We're left with limit as delta x is going to 0 of 2x delta x plus delta x over delta x. I think you can see there that if we use the plug-in system, we are going to click-up-in method, we're going to get a 0 over 0. So we factorize. Let's factorize and get this as limit as delta x is going to 0. Let's get that line again. Right. So if we factorize, we're going to have delta x in brackets, we're going to have 2x plus delta x over delta x. Then simplifying, I think we can see that this term here and that term there, they make a 1 because the number of a number, that's a 1. So in the final analysis, we're looking at limit of delta x going to 0 of 2x plus delta x. Then what is in bracket has become a kind of an expression or a binomial in terms of delta x, and you cannot get any undefined kind of situation there. Then you can plug in. So plugging in gives us 2x plus 0, which is equals to 2x. So not where we started from. We started from x squared. Now we have got 2x. It looks like we haven't lost anything we had. We had 2, yes, we have. We had x, yes, we have. So let's move to the second following situation. And then why I'm focusing on this thing of 2 and x, I want you to start thinking of some kind of pattern coming up or some kind of a special observation you can make there. So let's come to this one. This I'm not going to do for you. I'm going to ask you, I'm just going to give you a kind of, you are calculating again f. I'm going to give you a push start here. And then say there you are going to be calculating the limit of as delta x is going to 0 of x plus delta x to the power 3 minus x to the power 3. Now what we need here, we need, like in the quadratic situation, we need to know how to expand this. We need to simplify it accordingly. And if somewhere along the line we see that we are being presented, we can get something like this. If we evaluate, we need to know what to do and get there. So my encouragement to you is that do this calculation and see that you get to that fx prime is something like, it will be plus something there, x there, and that. And what I want you to do is that looking at f of x equals to x power 3. I want you to, at that point when you've got this done, try to compare these two and just think what you can. What do you think happened to this given function to get you to this kind of thing? All together? Okay. Now, what I really want to discuss with you, which is going to cover this thing, because I find this more interesting than the previous one, is this case when I've got x to the power n. All together? But for this case, there are a lot of things we need now, because I not said that binomial expansion is now not discussed in Maths 1 but in Maths 2. But we need some of those things here now. So what do we need here? I'm reminding you, but because we touched this when we're doing complex numbers. This one, n with that exclamation mark there. Can you see that? That you read it. You read that as n factorial. That's how you read it. But what is it? N factorial is a product of n and the number before n and number before that dash dash, continue with that kind of reducing by 1 until you get to 3, to 2, and to 1. That is what is n factorial. So in case you want to interested in getting 5 factorial, then you know that this is 5 times 4 times 3 times 2 times 1. All together. Okay. Then we have got two special numbers for 0. 0 factorial. Obviously, because 0 cannot do something kind like this. Then 0 factorial is equals to 1. That is a kind of a convention, a kind of gentle people's agreement. I'm trying to avoid to say gentleman's agreement because that is not politically correct these days. So this is also equals to 1 factorial. So 1 factorial and 0 factorial are both equal and equals to 1. That one you can just accept as a kind of a convention, as a kind of gentle people's agreement. Is that fine? Okay. So what do I want to know? What do I want you to know about this, which I'm going to use factorial here, is the following. There are two calculations like this one. This is not a fraction, please. There's no line there, anything. They just bracket like a matrix. All together. So how do I read this? I read this as M choose N. And also, this is a kind of a calculation. I remember very well. One of my openings, kind of, I think you took it as a joke. I gave you a problem, a kind of just, I don't know what you want to call it, but I gave you some kind of a problem which says, if you're given an alphabet of 2 letters, only 2 letters, and we're allowed to write words, different words with those 2 letters, combining 2 letters. You're allowed to repeat, like we've got, you can have, if the letters are A and B, you're allowed to write the word AA. You're allowed to write the word BP. So how many words can you write? This has got something to do with this. If you go and read your book, you will understand more what this has got to do with this. So, right. So how do you calculate this as a number? This is M factorial over M minus N factorial multiplied by N factorial. So why is this important for us? That's the interesting thing. Why is this important for us? Let's just look at something like this. Can you expand this? Tell me what you get. Expand this. Maybe let me use 3, like the one we had before. Can you expand this quickly? Expand that. Do you have the answer? Let me give you just 1 minute to do that. Please expand that. Right, this guy's got he's got the expansion ready. What is your expansion? X to the power 3
plus x squared y
plus x squared y
plus 2y x squared
plus 2y x squared
plus 2y squared x
plus 2y, what are you saying?
plus 2y squared x.
Let's say plus 2x y squared. Please try to write them alphabetical so that you can easily identify your like terms. 2, is it y squared or x squared?
That's y squared.
Y squared.
Yeah.
Y squared
Plus x y squared
plus x y squared
plus y power 3.
plus y to the power 3. That's your expansion.
Yeah.
But do you see that there are like terms there? One thing which makes it difficult for you to see like terms because you're not writing your letters in alphabetic order. If you're writing in alphabetic order, you could have given me this like this. Because you could see easily that you can simplify these 2 to 3x squared y. And these 2 to 3, what, to 3x y squared plus y cubed. All together. What do you see about this thing? What is interesting about this thing which you can see immediately? Huh? Nothing.
So no, it starts when you say the x to the power 3, it goes into when the x to the power 2, then you've got the y to the power 2.
I don't know whether it's what you are saying. Let's see. I think you can see that the powers of x are going down. Here, x is actual power 0. Do you agree? And here, y is actual power 0. And the powers of y start 0, 1, 2, and 3. All together. And the other thing plotted there, 3 plus 0 equals to 3. 2 plus 1 power for y here. 2 plus 1 equals to 3. What is this? This is 1 plus 2 equals to 3. 0 plus that equals to 3. That's a very important thing to note, because if you are required to do this expansion quickly, you check those things to check whether your expansion is very correct. If it works like that, then they're correct. Now, let's see whether you agree with me this. I can tell you for a fact that this expansion, the same expansion, is actually 3, choose 0. Look at this. 3, choose 0. 3, 0. X to the power 3, y to the power 0, plus 3, choose 1. X to the power 3 minus 1, y to the power 1, plus 3, choose 2. X to the power 3 minus 2, y to the power 2. If you check, 3 minus 2 plus 2 is 3. Plus 3, choose 3. Y to the power, sorry, let me say not y but x first. X to the power 3 minus 3, y to the power 3. Then we can come now calculate these calculations here, as we have decided that the calculations are this side. Let's say 3, choose 0. 0 factorial is 1. 3 factorial in numerator, there is 1 times 2 times 3. Do you agree? Over 3 minus 0 is 3 factorial. It will be 1 times 2 times 3. 0 factorial is 1. Don't even need to write it. If you look at this, this is 1. So the coefficient there is 1. So we've got x to the power 3, and the leading coefficient there is 1. And the y power 0 is what? Is 1. Plus 3, choose 1. Three factorial numerator to be 3 times 2 times 3. 1 minus 3 minus 1 is 2. So we've got 3 minus 1 is 2. So we've got 2 factorial 1 times 2. 1 factorial is 1. Don't even need to write it. Now, if you look at what has happened there, the final result will be what? 1 times 2 over 1 times 2 is 1. Then the final result is what? Is 3. This is what we've got here. So that will be 3, x to the power 3 minus 1, which is x to the power 2. Y to the power 1, which is y. Plus, come back here, we put our 2. Now, 3 factorial at the top is same thing there. 3 minus 2 be 1. 1 factorial is 1. So, for that part, we've got only 1 then. Times 2 factorial. Times 2 factorial, it will be 1 times 2. Again, these 2 and that one, they make 1, and you get another 3. So you get the plus 3 x 3 minus 2, 1, 4, 1. And that will 2. And then you can try the last one for yourself. I'm sure it's going to give you 1. So what are going to have there? You're going to have x to the power 0, which is 1, and the y to the power that. So you can actually expand with any value of n here. They say in this case, let's just temporarily consider positive numbers. Positive integers from, let's say, 2, 3, and so on. You can calculate any expansion using this kind of method, and the coefficients are calculated this way. In this case, this is a binomial coefficient for this. Is that clear? Okay. So actually what I've done here, I've actually given you also the method for doing the previous one. So now we see this n, we're not talking about n equals to 2 or to 3 to 4. We can go as far as 9, 10, and 100. We want to see if with something like that, how to get the derivative. All together. So now we've got the method, the 80 method. Right. Maybe just to make a short comment on what we said to this Kramer, or not Kramer's rule, Pascal's triangle. I see people here, they say they don't know what is Pascal's triangle. Let me just make a short comment about that. That we have, before I go further, let me just write this. Pascal's triangle is for expanding these binomials. How? Just check this. If you've got a plus b to the power 0, what is that going to give you? 1, is it? This is 1. If you get a plus b to the power 1, you know that this is going to give you a plus b. If you get a plus b to the power 2, you already know, you've seen it before, this is going to get a squared plus b, plus 2ab, a squared plus 2ab plus b squared. A plus b to the power 3, we've already seen from the previous calculations, gave us a cubed plus 3 a squared b plus 3 ab squared plus b what? B cubed. Now, if we look at this development downwards and you forget about the a and b, just focus on the coefficients, you'll get something like this. That's kind of a triangle. At the top there, you're going to have this coefficient 1. Here, you're going to have 1 and the 1. Next one, you're going to have 1, 1 plus 1, 2, and the 1. The next one, this one, you're going to have 1 for this coefficient here. 1 plus 2, 3. 1 plus 2, 3, and the 1. Then I can proceed with this. 1, 1 plus 1, 4, 3 plus 3, 6, 3 plus 1 is 4, and 1. This kind of a triangle, and you can see how it builds up, is called Pascal's triangle. Pascal's triangle. You can use it to expand the binomials, especially of positive powers, like 1, 2, natural numbers, 1, 2, from 0 actually, all numbers, 1, 2, up to n. And always, if the power is 0, you can see the number of terms is 1, so 0 plus 1. If the power is 1, number of terms is 1 plus 1, 2. If power is 2, 2 plus 1, you get 3. And so that, you must, I think that is handy for expanding such kind of things. So you don't really need to sit down in there. The only thing what you need to do now, using what I said to you before, how these powers of A and B combine, you can just go filling in the powers of A and B to get the right expression. All together, that's the Pascal's triangle. Right. So now let's move to calculating the derivative of this one and see where there's something interesting you can learn there. For this derivative, then we'll say, let's say y prime. In this case, y prime is our p of x prime. Another notation, we can use dp dx. I'm just using all the notations possible there so that you choose which one you want to use. All together. Then we'll say now limit as what? Delta x is going to 0. Then we've got that. What do we have there? We're going to have del x plus delta x to the power n minus x to the power n. So maybe let's create a kind of a division here. Let's put this way. What I want to do, let's work with this separately here, all together. Then we see what happens. So this is going to give us x plus delta x to the power n. According to what we saw, we're going to have n choose 0. N choose 0 always going to be 1. You can try it. That's right. Do you understand what I'm saying? So we're going to have x to the power n here. Then next thing, we're going to have 1, n choose 1. So in this case here, delta x will have power 0, so it's going to be 1. We'll leave it as it is, isn't it? But here, we're going to have x n minus 1 multiplied by delta x power 1. Do you agree with me? Okay. Then you come here and say plus n choose 2. Then it will be x to the power n minus 2 delta x to the power 2 plus n choose 3 n choose 3 x to the power n minus 3 delta x to the power 3 plus, I'll let this continue as far as n goes. So here I don't really mind whether n is 1000 or n is 100, it just continues, right? For our purposes, this is enough. Now, let's look at this. Now, let's work out this coefficient. This coefficient I work out here is to be n choose 1. It will be n factorial. Now it's going to be n by n minus 1 by n minus 2 dash 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 by 3 by 2 by 1. At the bottom here, we're going to have n minus 1 factorial. N minus 1 factorial will start with n minus 1. Remember now what I'm doing. I'm doing the definition of m choose n. Is it clear to you? So then it was followed by n minus 2 and then go on until 3 times 2 times 1. The other product will be n factorial of 1, which is 1, doesn't matter. Altogether, it's 1, you don't write it there. times 1. So what we have now is that this from here, n minus 1, up to 1, and from there up to there, that gives us a 1. And the 1 times n, which is n. Then we are saying this coefficient here, the next coefficient here is n, x to the power n minus 1, and the delta x to the power 1. If you look at the binomial, sorry, why is this 3? I'm asking you, why is this 3? Mistake, isn't it? So please look out for that. Look out for that. This is not 3, it's n. Do you agree with me? Okay? So that is n. If you look at the binomial power 2, even the binomial power 3, it started with the x power 2. The immediate coefficient there was 2. With 3, it started with x power 3. Immediate coefficient there was what? Was 3. So it looks like the pattern follows here, isn't it? That is very important to observe. Then plus, then we come to n choose 2. N choose 2. Let me pick duster here. Let's clean this one. What we have here? Right. Here we're going to have, let's have a straight line there. For that, then you say n choose 2 is that. What is this? It's going to be n factorial at the top, n minus 2 factorial, and the 2 factorial. Let's write 2 factorial here. 1 times 2. That's 2 factorial. Then this one will be n factorial as n minus 1, n minus 2, dash, 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 3, 2, 1. Do you agree? Then the other one will be n minus 2 factorial, which means going to start here. N minus 2, dash, 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 up to 3, 2, 1. Now, looking at that, simplifying from here up to there is what? Is the same thing as we have there. So that will create us a 1. So what we're left with here? We're left with n minus 1 over 2 factorial. So let's write it here. Let's write it here. It's n, is n minus 1 over 2 factorial. Then what's going to happen here? We're going to have x to the power n minus 2 and the delta x to the power 2. Plus, I'll leave this one for you. This one, I'll leave it to you for you and tell you, you must expect n minus 1, n minus 2 over 3 factorial. Just do it. I want you to have a feel of it. Do it and see what other. But not now. Do it later as homework. Let's continue with this one. So now, what we have here is enough for our presentation. So now let's continue here. Now if we continue here, let's maybe write this here. Say limit as delta x is going to 0. Get a line here. Then you've got here, put that line there, over delta x. So what we have now for this expression, we just write this expansion and then continue the dash, 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 all together. Then we subtract that one. Let's write it in brackets, actually, this one. Let's write it in brackets and say, brackets, xn plus n, xn minus 1, delta x plus n minus 1 over 2 factorial x n minus 2 delta x to the power 2 plus dash dash close the brackets minus x minus n. Please feel comfortable that you have got that right there. Are you comfortable with that? Check it. Right. If you're comfortable with that, I think you can see that in the brackets we've got xn, and outside the brackets we've got minus xn. So in other words, we've got like terms there, and there's a minus sign, and then they should make us 0. What are we going to be left with? We're going to be left with this kind of an expression. Going to calculate limit delta x going to 0 of n brackets, sorry, why did I write that bracket there? That bracket is not necessary. N x to the power n minus 1 plus delta x plus n brackets n minus 1 over 2 factorial x n minus 2 delta x power 2 plus dash dash dash. This continues to whatever n is. So let's write our fraction there. That's what we have. Now we can see you cannot plug in 0 here because you're going to get 0 or 0. Is that clear to you? Yes or no? Now, notice one thing. This has got delta x power 1, power 2. Then the rest of the terms there are going to contain delta x to a certain power. Are we there? Now, but if we plug in 0, we're going to get this. But we can factorize. Let's factorize and take out 0 as a common factor in the numerator and see how does that help us. If we factorize, extract delta x as a common factor, we've got inside here n x to the power n minus 1. Do you agree? For the first term. Next one, you can tell me something. Tell me what should I write? The next term, what should I write? I'm asking you. We have taken out delta x as a common factor. So what will be the next term here? N. Okay, let me write that one first. Over 2 factorial. Then what next? X to the power n minus 2. Next? Delta x. Then let me check with you. The next term here will contain delta x to the power. Yes?
The delta.
Yeah, the delta x to the power. Here it will be 2. The next one, power 3. The next one, and so on. Isn't it? So the rest of the terms have got delta x. So let's close that bracket there. Let's just say dash, dash, dash. Now, but this one and this one, they make us say 1. All together. Let me highlight them there so that you can see them. This one and this one, they make us a 1, which means in the next line, we're not going to have a rational expression. We're going to have a kind of polynomial in terms of delta x. Then we've got n here, x to the power n minus 1. Let's put it in brackets. Plus n minus 1 over 2 factorial x to the power n minus 2 by x to the power So delta x to the power 1, sorry, to the power 1. From what I said before, I'm expecting the next one to be n minus 1, n minus 2 over 3 factorial delta x to the power, sorry, x to the power n minus 3 delta x to the power 3 plus dash dash going on. Do you agree with that? Why not? Delta x squared. Good. Now you are paying attention. Delta x squared. This is delta x squared. Do you agree? Okay. Delta x squared. Right. So now from there onwards, we'll call delta x3 and so on. But now, because we don't have a rational expression which is going to give us an undefined entity like this one, what can we do? We can just plug in delta x. But if we plug in delta x, we're going to plug in 0 there, and 0 and so on. So which means now we're going to have here limit, sorry, here I forgot to put delta 10 to 0. Limit as delta x is going to 0 of what? Of n x n minus 1. This times that 0 plus 0. There, let's times that plus 0. So plus 0, 0, 0 going that way. Now calculating the limit of this does not depend on delta x. So in terms of delta x, this is a constant. So this limit is going to be n x n minus 1. And then we stop. I think now when we stop here, we must start thinking of where we started from. Let's see. We started with a p of x, which was x to the power n. And we've arrived at p prime of x, which is equal to n x to the power n minus 1. And this is beautiful. And this is beautiful. When we look at these things and think properly and see what has happened, you remember before, I said we started with a y, which was what? X power 2. We ended up here with y prime, which was equals to 2x, which I can write as power 2 minus 1, which is actually what you are saying. You are saying this is 2x. Then I can go further and say the first one, the one before this one was y to the power x power 1. And here we ended up with 1. I can claim that this was 1 multiplied by x to the power 1 minus 1. What am I trying to do? I'm trying to mimic what I'm seeing here. You understand what I'm saying? Then I come here and say 1 times x to the power 0, and that is 1. I can even say the one before was a c. A c is equal to a c multiplied by x to the power 0. Do you agree? A c is the same thing as c multiplied by x to the power 0. Do you agree? Then I can say this now. The prime this side was c multiplied by 0 x to the power 0 minus 1. And then I've got c multiplied by 0 multiplied by 1 over x. Remember, this is going to give you x to the power minus 1, and the power minus 1 is 1 over x. Then when I come here, I will say c times 0 is 0. Multiplied by 1 over x is 0 over x. And then this gives us 0. Now if you follow this pattern from here, to there and go on there, you have got what we can call, what is actually usually called the power rule for differentiation. What did I say? What did I say? I'm asking you to repeat what I said. Nobody can repeat that. Then you're not listening to me. I said if you follow this pattern now, from this situation to there, to there, to there, and you see a kind of a pattern. Remember I said at the beginning, observe if there are coming some patterns coming up here. I'm saying if you start from here to there, and end up with something like this, there's kind of a pattern there. And the pattern is with the powers which you're getting. I'm saying if you look at that pattern and observe it and say, okay, you come up with something which you call the power rule for differentiation. What does the power rule for differentiation say? The power rule says, differentiation says, once you've got a function of x, something like this, to get the derivative, at this stage, what we have seen, we might as well leave that calculation. That calculation was important to get to this. But the mechanics of it now, this is now mechanical. It's not like with calculating limit. What you can do, you can take this n down here, come up with the same x, but reduce this by 1. Then you've got the derivative. That is called power rule for differentiation. That's power rule for differentiation. And that is important. So now you get to any polynomial or any power of x, you can apply this. In this case here, that binomial expansion we dealt with, that n could be even a rational number. And it works out to be the same. So now, let's see whether you have got the message. Find the derivative of this one. I just want to see how many people got the derivative, the message. Find the derivative for this one. One question must ask yourself, this guy, we were talking about powers, but now it's coming with a radical sign here. We haven't discussed this. That's what the student will say. We haven't discussed this, but how come? Obvious, it means there's maybe some kind of implicit relationship between powers and this radical sign altogether. So you do the translation. Once you do the translation, you find the equivalent of this in terms of powers. Then you apply the power rule. Am I making sense? Okay. So who has got the answer ready for me? First of all, show me the translation to kind of the power version. Yes, what is the translation?
X to the power of.
He says x to this radical sign is equivalent, translation in power language, this is power half. The only thing I can check with you, do you agree or you don't agree? Do you agree? Okay. So if you agree, then you can now try to do this kind of a thing. How do you do it? Can you tell me what to write?
X.
All right, half x to the power half minus 1. Please don't be fast for slow learners. Né? Yeah, put all the steps at the beginning, then you can summarize at the end. All together. So now, this is half minus 1. It's like 1 half minus 2 halves. What is that? What does that give us? Come again? Minus 1.5. Minus a half. Okay. X minus a half. Do you agree? Do you agree? Okay. Do you agree? Okay. So you've got that. Now, using this kind of, that x to the power minus n is equals to 1 over x to the power n. As you can see, the rules of exponents are back. So which means some of the things you know before, they are still very important here. So now using that, you can now say this is half multiplied by 1 over square root of x, because this one will be 1 over x to the power half, but x power half squared. I'm just writing it this way so that it's sort of like easy to handle. Then we've got 1 over 2 square root of x. Then what done? Okay, I think now I can say, go and take your textbook, look at any expression which is a polynomial or powers of a radical sign which you can translate to power and differentiate them this way. Then we are done. Are we together? Okay. So I think I'm going to stop there, hoping that people, we have seen exactly what we've done. I think just summarizing, we started with those functions. Are we together? And 16 now, I think this and more is answered. Polynomials and more. When we get to those radical signs, is actually a bonus on what we've learned from polynomials and to differentiate that. Are we together? Now the answer to more there is there. So then we follow the constant function, which I said this is one thing which you must never forget. You can forget everything else, but to say the rate of something which is the rate of change of something which is constant is 0 must live with you, and you must apply it in everyday life. I mean, that is kind of something which you can use every day in your life. Then we came on to the linear functions, and you observe that the derivative of a linear function is actually its gradient. Altogether. So this is what we've covered. The cube, this is the homework I gave you, but actually this somehow has been done for you, not using the linear quotient, but using the power rule. Altogether. So when you finish doing this one, you must make sure that the result you get here actually agrees with your result, final result, what we've called power rule. Altogether, guys. So this is the final discussion, including all those things of factorials and so on, and up to there. So otherwise, at that point, guys, I would like to say thank you for listening. I hope you have time to go and sit down and soak yourself into this thing, because that is what is lacking. You have got all the information in front of you, but you guys are not soaking yourself into this information, and that is delivering bad results. But anyway, let's be positive and hope that people are going to stand up to the call and they do something. Thank you for listening. Let's meet in the next session. Goodbye.